Previously, we had discussed about representing a system of linear equations in a matrix form as a single matrix equation, and then we also solved it using the matrix inversion method. And in that process, we computed the cofactor matrix and then the adjoint matrix, and from the adjoint matrix, we also determined the inverse of the coefficient matrix, and then we eventually used that inverse of the coefficient matrix to solve for the variables x, y, and z, and we had got the solution for these set of equations, the first set of equations, as x equal to 0, y equal to 1, and z equal to 2. So we got the solution as x equal to 0, y equal to 1, and z equal to 2. We solved this using matrix inversion method in the previous session. Now, one thing I want to highlight today is that if we have a set of equations where the numbers to the right side of the equality, if these are such that at least one of them is non-zero. Suppose we have a set of equations wherein even one of these numbers is non-zero, then we call these equations as non-homogeneous. But if all these numbers on the right side of the equal to, okay, if you have a set of equations wherein all the numbers to the right side of the equal are 0, then we call such a set of equations as homogeneous equations. So the second one here is a set of homogeneous equations, and the first one here, which we solved in the previous session, is a non-homogeneous set of equations, or the equations represent a non-homogeneous system. So if all these numbers are 0, then the system of equations represents a homogeneous system. If even one of these is non-zero, then the system is non-homogeneous, right? What is the implication of the system being homogeneous or non-homogeneous? The equations which represent a homogeneous system, as in this case, will always have a trivial solution as x equal to 0, y equal to 0, z equal to 0. Or if it is only with two variables, then x equal to 0, y equal to 0, and so on. So we discussed earlier that a system of equations may have a unique solution if the determinant is non-zero. That means if the coefficient matrix is not singular. In that case, there is a unique solution. Or the determinant could be equal to 0, and there is a chance that the system has an infinite number of solutions. And the third case is when the determinant would be 0 and the system has no solution at all. That means there is no intersection of those planes or straight lines. So in that case, we say there is no solution at all. In the case of a homogeneous system, that third case of no solution does not occur, because there will always be a point of intersection at the origin. So the equations or the lines or the planes would have an intersection at the origin where the variables, all the variables x, y, and z, if it's 3-dimensional, if it's 2-dimensional, only x and y, and if it's 4-dimensional, all the 4 variables and so on, all of them would be equal to 0, which corresponds to the point in the n-dimensional space as the origin. So a homogeneous system always has a trivial solution at the origin. That means even before we begin to solve it, we know for sure when we look at a homogeneous set of equations or a system of equations representing a homogeneous system, that the origin is a solution. And clearly, what is the solution? It's the values of x, y, and z that satisfy the equations. So if the right hand side of these equations is equal to 0, then obviously if you put x equal to 0, y equal to 0, and z equal to 0, then we'll get 0 in any of these equations, right? So a homogeneous system has a trivial solution at the origin. So that's the first observation we make about a homogeneous system. So what we have at the top here, this is non-homogeneous, and the system that we have at the bottom here is a homogeneous system. And for a homogeneous system, a trivial solution exists at the origin. That means x equal to 0, y equal to 0, and z equal to 0 in this particular case, because we have 3 variables, is going to be a solution. So is a solution even before we solve it, right? But if it has multiple solutions, maybe then in that case, in addition to x equal to 0, y equal to 0, and z equal to 0, there could be other solutions as well, as in this particular set of equations. This particular set of equations that I've shown here, these have infinite possible solutions. And we will see later on that these are indeed having infinite solutions. And I will also show you, not in today's lecture video, but in the next video, how to determine that the system of equations has multiple solutions or not. Okay, we'll discuss that as well. But today we will graphically depict and show that this particular system of equations, which represents a homogeneous system, indeed has an infinite number of solutions. But a homogeneous system will always have the origin as a solution. So the system of equations representing a homogeneous system will always pass through the origin. That's what it means. That means every plane or every line will pass through the origin, as you see from this video here. Okay, so this particular diagram here is what we have seen in the previous session, representing this non-homogeneous system, where we got the solution as x equal to 0, y equal to 1, and z equal to 2. That was the point of intersection. And this particular system had a unique solution, which is this 0, 1, and 2. But what we are seeing today, this particular set of equations, which represent a homogeneous system, is having infinite possible solutions, and one of the easiest or trivial solutions is the origin. Okay, so you will see for yourself now from this video that this particular system of equations, which I have plotted the planes here, indeed all these planes representing each of these equations are passing through the origin. So the first equation is represented by the green plane, the second equation is represented by the red plane, and the third equation is represented by the violet plane. And one more thing I want you to notice is that I've written this y coefficient in red. Sometimes we may have equations where a particular variable does not exist. For example, this equation is simply 4x plus 6z equal to 0. That means the coefficient of y is 0. So this equation is represented using only the two variables x and z. So the coefficient of y is 0, and just for completeness I've included that in the equation. Even if you write it as 4x plus 6z equal to 0 would be fine. But when we write it in matrix form, we need to make sure that we are writing the correct coefficients in the correct positions, because the matrix will have all the coefficient of x in the first column, all the coefficients of y in the second column, and all the coefficients of z in the third column. So have a quick look at this plot of these equations so that you get an idea as to where the solution lies in this particular homogeneous system. So you clearly see that all the planes are crossing each other and they are passing through the origin. And I will illustrate in the next few slides that the crossing is not a point, but they all cross each other at a line. So that entire line forms the solution space. So that means all points which lie on that line will give us the solutions to these equations. That means any point on that line where the intersection takes place falls on all the three planes. So therefore this system of equations has infinite possible solutions, and one of the solutions is the origin, which is x equal to 0, y equal to 0, and z equal to 0, which you can clearly see from this depiction, right? So you clearly see here, So let me go back a little bit. So you see here, all of them are passing through the origin. So the origin is always a trivial solution in the case of a homogeneous system. Okay. Now what we are going to do today is we'll try to solve these system of equations, whether it is non-homogeneous or homogeneous, by our next method of finding the solution, which is called as the Cramer's rule. And I'm sure many of you would have come across and used the Cramer's rule in solving equations in your earlier courses, like your electric circuits 1, wherein you would have solved the nodal equations or mesh equations or KVL, Kirchhoff's voltage law, or Kirchhoff's current law, and you would have used Cramer's rule to solve the current or voltage equations. So I'm sure most of you would have been through it, but for the sake of completeness, we will cover the Cramer's rule in this course as well, and that is what we are going to do next. And what I've depicted here is a system of homogeneous equations containing only two variables, x and y. Previously we have seen the equations with three variables, x, y, and z. Now we have the system with only two variables, x and y. I'm going to demonstrate the usage or the procedure to use Cramer's rule using the two variable system, and then we will proceed to the case of three variables as well. So we are going to solve these equations, which is x plus y equal to 0 and 2x plus 5y equals 0. And because both the numbers on the right side of the equal to in this system of equations are equal to 0, this constitutes a homogeneous system with two variables. And clearly you can see in this particular case the intersection occurs at the origin, and therefore the origin is a trivial solution. Now, since these equations are having only two variables and they are depicted in a two-dimensional plane, so each of these equations represents a straight line. So the first equation, x plus y equals 0, is representing this red line, and the 2x plus 5y equal to 0 is representing this blue line. And what we'll do is, we can clearly see that the origin is indeed a solution. It is a point of intersection for the two lines. And even before we solve it, or even before we see these plots, when we look at a system of homogeneous equations, we know that the origin is definitely one of the solutions. It could be that other than the origin, there are other solutions as well, but the origin is definitely one of the solutions. So we call it as the trivial solution. That means trivial means easy solution, because we know it just by looking at the equations. So let us try to solve these equations using Cramer's rule, which is our next method that we are going to use. So we're going to solve this using Cramer's rule. And to solve using Cramer's rule, we are going to first represent these equations in matrix form. So we write the matrix equivalent of these equations. So it is 1, 1, 2, 5. That's our coefficient matrix. And the variables are x and y. And the right-hand side is having 0, 0. So the values on the right-hand side of the equal sign is 0. So when we have this B vector, right, so that's our coefficient matrix A. So that's our vector of variables, which we denote as x, and that's our vector on the right side, the numbers on the right hand side of the equals, which we denote by the vector small b. So this equation is written as ax equals b, and we are going to solve this using Cramer's rule. And to solve it using Cramer's rule, what we do is we first compute the determinant of the coefficient matrix. So we write 1, 1, 2, 5, and compute the determinant. And we'll call this determinant as simply delta. The determinant of the coefficient matrix, or the matrix A, is delta, or we denote it as delta, and in this case it's going to be 1 into 5. So we just do the cross multiplication, 1 into 5 minus 2 into 1. That's 1 into 5 is 5, minus 2 into 1 is 2. So we get the determinant as equal to 5 minus 2 is 3. So the determinant is not equal to 0, and therefore this particular system of homogeneous equations, or this particular system of equations representing a homogeneous system, is having a unique solution, because the determinant is not equal to 0. It's equal to 3. That's not equal to 0. So it has a unique solution. And to find the solution using the Cramer's rule, we will next find what is called as delta 1. We denote it as delta 1, and we obtain delta 1 by computing the determinant of the A matrix by replacing the first column of the A matrix with the vector B. Yani we'll replace the first column with the vector B. So we'll remove this 1, 2, which is present in the first column, and in place of this 1, 2, we'll put the vector B, which is 0, 0, okay? And keep all the other elements as it is, and then compute the determinant. That would give us delta 1. So the first column becomes 0, 0, which is the B vector, and the second column remains the same. That's 1 and 5. And we compute the determinant of this, and obviously when you do the cross multiplication, you'll get 0 minus 0 is 0. And similarly for delta 2, we'll compute the next component called as delta 2, which is the determinant value of the A matrix with the second column replaced by the vector B. So we'll remove this 1, 5, and in place of this 1, 5 in the second column, we'll put the B vector 0, 0, and keep all the other elements as they are. So we'll keep the first column as it is, so 1, 2, and the second column gets replaced with B, and again the determinant for this 1 into 0 is 0, minus 0 equals 0. So we get delta 1 equal to 0 and delta 2 also equal to 0, and the determinant of the original A matrix is equal to 3, which is not 0, and therefore it has a unique solution. Now we want to find the values of x and y, and according to Cramer's rule, we solve x and y as x equal to delta 1 by delta. So if you notice delta 1, we computed delta 1 by replacing the coefficients of x. So this 1 is the coefficient of x in the first equation, and this 2 is the coefficient of x in the second equation. So we removed the coefficients of x and replaced them by the vector b to compute delta 1. Similarly, to compute delta 2, we removed the coefficients of y. 1 and 5 are the coefficients of y, and replaced them by the vector b to get delta 2. So x is obtained as delta 1 by delta, which in this case is equal to 0 by 3, which is equal to 0, and y is equal to delta 2 by delta, which is also equal to 0 by 3, which is equal to 0. So the solution is x equal to 0, y equal to 0, which is nothing but the origin. And because this system of equations is having the determinant value, the coefficient matrix has a determinant value equal to 3, which is not equal to 0, it has a unique solution, and that unique solution is at the origin. So that's the only solution for this system of equations. That means these lines do not intersect at any other point. So the only point at which they intersect is the origin, which corresponds to x equal to 0 and y equal to 0. So that's how you would solve a system of linear equations using Cramer's rule. Now we will extend this idea to a system which has 3 variables, and we will use the same set of equations which we used in the previous session for the matrix inversion method, and check whether we get the same solution. So we are going to use this first set of equations and see if we get the same solution using Cramer's rule as well. So let us do that. So now I have written down that system of equations using the matrix representation. So in matrix form, so we have that's our A matrix A, and that's our vector of variables x equals the vector B. And obviously because these elements of B are having non-zero numbers, it's a non-homogeneous system, right? Even if one of these numbers is non-zero, then this system, these equations represent a non-homogeneous system. So let us now use Cramer's rule to solve these the system of equations. And the first step we'll do is to find what is called as delta, which is nothing but the determinant of A, which is we've calculated this earlier in the previous session as well. Let me quickly write that. So that would be 1 into 2 plus 3. Minus of minus 1 will become plus 1 into 4 plus 1 plus 3 into 12 minus 2. So that becomes 5 plus 5. 12 minus 2 is 10 into 3, 30. So plus 30, which is equal to 40. So we get delta equals 40, which is not equal to 0, and therefore as we have solved and seen previously, this system of equations has a unique solution. Right now let's find delta 1, delta 2 and delta 3, because we want to find x, y and z. So to compute delta 1, we are going to replace the first column, which is containing the coefficients of x, with the vector b, and then compute the determinant. So it would be the determinant with the first column replaced by the vector b and all other columns as it is. So it will be minus 1, 2, 3, 3, minus 1, 1. Right? And when we compute this determinant, we'll get this determinant to be equal to 0. So let's write it down. It would be that's equal to 5 into 2 minus 3. So that's 2 plus 3. And I'm going to compute the determinant using the first column. As I said before, the determinant can be computed using any row or any column. So I'm going to use the first column in this case because there's a 0 here. So it makes the calculations easier. So the 0 is going to have a positional sign of minus. So minus 0. 0 into anything is 0. So we don't bother about it. And plus 5 into, so we close this, it's this 5, so we close the row and the column, so that leaves us with these 4 numbers. Minus 1 into minus 1 is plus 1, that's 1, minus 2 into 3 is 6, so it's 2 into 3 will be 6. So we get 2 plus 3 is 5, 5 into 5 is 25, so that's equal to 25 minus 0 plus 5 into minus 5 is minus 25, which is equal to 0. So we get the value of delta 1 to be equal to 0. Similarly, we will compute the value of delta 2 by replacing the second column of the A matrix with the vector B. So delta 2 would be, delta 2 is equal to the determinant with the second column of the coefficient matrix replaced by the vector B, 5, 0, 5, and all other elements kept as they are. So that's 3, minus 1, 1. And when we compute the determinant for this, you would get 1 into 0 plus 5 minus 5 into 4 plus 1 plus 3 into 4 5s are 20 minus 0. So that would give us a determinant value delta 2 to be equal to 40. So that 0 plus 5 is 5. 4 plus 1 is 5 into minus 5 is minus 25. Minus 25 plus 5 is 20. And this is 60. 60 minus 20 is 40. So we get delta 2 to be equal to 40. Similarly, we'll now compute delta 3. And for delta 3, we will replace the third column of A with the vector B and compute the determinant. So for delta 3 would be, the first two columns would be as they are, so we'll keep them as they are, 1, 4, and 1, minus 1, 2, 3, and then we have the third column which we will replace by the vector B and compute the determinant. Now with this we get the answer as 1 into 10 minus 0, minus of minus 1 will become, that's minus of minus 1 into 20 minus 0 plus 5 into 12 minus 2. So we get 10 plus 20 plus 50, that's equal to 80. So we get delta 3 to be equal to 80. And from these three values of deltas and the determinant value of the original matrix, we can now compute or calculate the values of the variables x, y, and z. So x will be delta 1 by delta, which is 0 by 40, which is equal to 0. Similarly, y is equal to delta 2 by delta, which is 40 by 40, which is equal to 1, and z equals delta 3 by delta, which is 80 by 40, which is equal to 2. So we have our solution as x equal to 0, y equal to 1, and z equal to 2, which is exactly the same answer we got using the matrix inversion method, right? Now you might ask why, it looks like the Cramer's rule is much easier than the matrix inversion method, and it looks much simpler and shorter, but still why do we use the matrix inversion method? That's because sometimes the Cramer's rule cannot be used to solve the system of equations, in which case we'll have to find other methods to solve the equations. So as we will see for the second example of the that we have used as the set of equations representing a homogeneous system, we will see that Cramer's rule could not be used for solving those equations, even though we know that because it's a homogeneous system, it does have a trivial solution at the origin, and in fact that particular system has infinite solutions. But still, Cramer's rule cannot be used to solve that second set of equations, which is depicted here. So this system of equations representing a homogeneous system, we know for sure that it has one solution at the origin, plus it also has an infinite number of solutions, which is represented or given by points on a line that passes through the origin. But we will see that this system of equations cannot be solved using Cramer's rule, even though Cramer's rule seems very simpler, much simpler than the matrix inversion method. Why are we studying so many different methods? It's because some some equations could not be solved by one of the methods, so we'll need to look for alternative methods to solve those system of equations, because even though they might have solutions, the particular method may not be able to solve that particular system of equations. And also we choose a method of solving the equations depending on the complexity, the computational complexity, or the time it takes to get the solution, and so on. Okay, but let's talk about those things at a later stage. Let us now focus on trying to solve the system of equations representing the homogeneous system using Cramer's rule, and see what pitfall we fall into. So we have the system of homogeneous equations, which I had shown earlier, where we have this variable, the vector b containing all zeros. So therefore, this is a homogeneous system. And we'll try to solve it using Cramer's rule. To solve it using Cramer's rule, we will first compute delta as the determinant of this A matrix. So the determinant of A, which is 2, 4, 1, minus 1, 1, minus 2, 4, 0, 6. All right. And when we compute this determinant, we get 2 into 6 minus 0 minus 4 into minus 6 plus 8 plus 1 into 0 minus 4. So what do you get? So 2, 6, that's 12. 8 minus 6 is 2. 2 into minus 4 is minus 8. And that's minus 4 into plus 1 is minus 4, which is equal to 0. Now, when you look at this, you can clearly see that the determinant of the coefficient matrix is equal to 0. And when the determinant of the coefficient matrix is equal to 0, it means one of two things, one of two possible things. The first is that there is no solution at all for these equations, or the system of equations has infinite possible solutions. And in this case, because it's a homogeneous system, no solution is not an option. It's not possible for it to have no solution, because the origin is always a solution for homogeneous equations. So it's not the situation of no solution here, but the situation of no unique solution. That means it has multiple solutions which satisfy these equations. Okay? And to understand that, let me show you the plots of these equations once again and illustrate that this system of equations indeed has infinite possible solutions. So if you look at these equations and the plots of these equations, we see that the three planes, the green plane, the red plane, and the violet plane, they all intersect at this line. So all points that lie on this line are solutions to these system of to these equations, or the points of intersection to these planes. So any point on this line here, that's the line which represents the intersection of all the three planes. Any point on this line lies on all the three planes. So all points that fall on this particular line of intersection is a valid solution to this system of equations. And the origin is definitely one of the solutions, because all the three planes pass through the origin as well. So this line itself, the line of intersection, passes through the origin, and therefore the origin is one of the solution, and all other points that lie on this line are solutions. So this particular system of equations has infinite possible solutions, and because it's a homogeneous system, one of the solutions, which is a trivial solution, is the origin. But clearly, because the determinant is equal to 0, we cannot solve it using Cramer's rule. So we'll need to find other methods to calculate or to find the solutions of these equations. Simply because in Cramer's rule, we find, say, for example, x equal to delta 1 by delta. And delta 1 obviously is also going to be 0, because when we replace the entire first column with these zeros, then the determinant is going to be 0. If we have a matrix in which an entire row or an entire column is having zeros, the determinant value will be equal to 0. So delta 1, where we have all zeros in the first column, will evaluate to 0. Delta 2, where we have all zeros in the second column, will also evaluate to 0. And delta 3, where we have the third column with all zeros, will also evaluate to 0. And delta is also equal to 0. So that means when you calculate x as delta 1 by delta, we will get it as 0 divided by 0, which is undefined. 0 by 0 is undefined. Similarly, when we compute for y as delta 2 by delta, we will get it as 0 by 0, which is also undefined. And similarly, z will be equal to delta 3 by delta, delta 3 by delta, which will also be 0 by 0, which is also undefined. So Cramer's rule cannot be used to solve these system of equations, and we'll need to figure out other methods to solve these equations. And clearly, we see that this system of equations has infinite possible solutions, and all the solutions lie on this particular line. So let me mark that line. So this line over here represents all the solutions. So all points that lie on this line, right? All of them, just marking a few of them. All these are solutions to the system of equations, because the solutions of these equations are nothing but the values of x, y, and z that would satisfy these equations, or the points which are common to all the three planes. So all these points are common to all these three planes. All points that lie on this particular line of intersection fall on each of these planes, and therefore they are all solutions. But clearly, Cramer's rule cannot be used to solve the system of equations, and we'll need to look for other solutions, other methods to check whether the solutions are multiple solutions or no solution. So whenever we see that the determinant is equal to 0, then we have two options. One is that there is no solution, and the other is that there are infinite possible solutions. So if the determinant of coefficient matrix is equal to 0, then either of the following two cases is true. The first is there is no solution, and the second is that there are multiple solutions. Now, how do we know which of these statements is true? That we will investigate in the subsequent video, and we'll need to use other methods to solve these equations and to figure out whether the first condition is true or the second condition is true if the determinant is equal to 0. That means the determinant being equal to 0 means that the coefficient matrix is singular, and in that case it could either mean that there is no solution, that means there is no point of intersection at all, or there are multiple points of intersection, as in this case. So we have multiple points of intersection at which these three planes meet or intersect, right? So we will need to work out and see which of these conditions is true, and I will show in the subsequent video, in the next video, how a different method called as Gaussian elimination. We will see in the next video a new method called as the Gaussian elimination. So we'll discuss in the next video. We shall discuss Gaussian elimination. And I will take you through the steps involved in the process of Gaussian elimination, and we will do it for different types of equations, and show that under what conditions, after performing the Gaussian elimination, what should we observe in the result to determine whether there is no solution or there are multiple solutions, or there is a unique solution to the system of equations that we are trying to solve. It could mean one of these three conditions. So the first condition is that the determinant is not equal to 0, and in that case it has a unique solution. And the other cases are when the determinant is equal to 0, resulting in a singular matrix, and with a singular matrix there are two possible scenarios. One is there is no solution at all, or there are multiple possible solutions, and we can fix one of the variables and find the values of the other two variables, and so on. So we can find those multiple possible solutions. But even before we solve those and find those multiple solutions, we would first need to determine which of these conditions is true for the given set of equations if the determinant of the coefficient matrix turns out to be equal to 0. Okay, we'll talk about these in the next set of video, and we will discuss in detail the process of Gaussian elimination to solve the linear equations, as well as to determine which of these conditions is true. In this section, I will discuss about Gaussian elimination, and in particular, the focus of this section would be on the definitions and terminology related to Gaussian elimination, and also towards the latter part, I would focus on how to interpret the final matrix that we get at the end of Gaussian elimination. The process of Gaussian elimination itself would be discussed in the subsequent video, but the focus of this short clip would be restricted to the definitions and terminologies associated with Gaussian elimination, and also with the interpretation of the final result or the matrix that we get at the end of Gaussian elimination. So the first definition we see here is the augmented matrix. What do we mean by the augmented matrix? Given a system of equations which has been represented as a matrix equation, where we have the coefficient matrix A, the vector of variables x, and the vector of numbers on the right hand side of the equality, which is denoted by the letter B. Now the augmented matrix is nothing but the concatenation or the joining of the coefficient matrix and the vector B. So the augmented matrix is nothing but a matrix where we join the concatenate the coefficient matrix and the vector B. So that is the notation for the augmented matrix. So the augmented matrix would take the form for the above matrix equation as 1, -1, 3, 5, 4, 2, -1, 0, 1, 3, 1, and 5. So the augmented matrix has two parts. One is the A matrix and the other part is the B vector. So we have here, let me rather draw it as a continuous line here. So we have on the left hand side here, which is the A matrix, concatenated or joined by the B vector. Together they form what is called as the augmented matrix. Now in Gaussian elimination, the first step is to get the augmented matrix from the system of equations, and then we perform some operations on this augmented matrix. We call this as elementary row operations. We perform certain operations called as the elementary row operations, and we get another matrix at the end of these row operations which has a specific form. What are those row operations? I will talk about that in my next clip, but let us focus only on the terminology as well as the interpretation of the final output we get at the end of Gaussian elimination. So when we perform these elementary row operations, we get another matrix which has a form. For this particular matrix, it will take these values: 1, -1, 3, 5, 0, 6, minus 13, minus 20, and 0, 0, 40 by 6, and 80 by 6. So at the end of these row operations, we get another matrix which we call as the row-echelon matrix. It's called as this matrix here on the right hand side is called as the row-echelon form of the original matrix. So the original augmented matrix is representing the original set of equations, and after performing some row operations, we get another matrix which we call as the row-echelon form of the original matrix, row-echelon form. Now, if you notice the row-echelon form matrix, you notice again it has two parts, and we'll denote the first part here by the letter capital R, and the second part here, this vector on the right side, is called F. So the row-echelon form or the row-reduced matrix is composed of two parts. It's the concatenation of two matrices, which is called as the reduced coefficient matrix R, and another vector where the B vector has got changed to the F vector now. So basically the elementary row operations convert or transform the augmented matrix AB to another matrix RF. Now a few properties that you see from this row-echelon form or the reduced matrix is that all numbers below the diagonal are now 0. So that's your diagonal elements. All numbers below the diagonal have been reduced to 0, and when we have such a format of the matrix, we call it as the row-echelon form. So in the row-echelon form, all numbers below the diagonal part are converted to 0 or transformed to 0. So in such a case, we call this matrix as the reduced matrix, or the row-echelon form of the augmented matrix. When converting the augmented matrix to the row-echelon form matrix, we will perform these row operations on the augmented matrix, that is, and during these operations we will use the diagonal positions, not the diagonal element itself, but the diagonal positions of the augmented matrices coefficient part, the A matrix of the augmented matrix. These positions will be used as references, which we call as the pivots. So these positions here on the diagonal of the coefficient part of the augmented matrix, these are called as the pivots. So we will use these positions to do our row operations, or we will use the values of the numbers present in these positions as our references to perform our row operations in the process of converting the augmented matrix to the row-echelon form matrix. So that's the second definition that you should be familiar, and that is what are the pivots or the pivot positions. The next information that you should know is that the augmented matrix AB and the row-echelon form of the augmented matrix RF, they are called as equivalent matrices. They are called as equivalent matrices. They are equivalent. So these are equivalent matrices. What do we mean by that? It means that if either of these have a solution, then the other also has a solution, and that solution will be identical. So if AB, the augmented matrix, has a solution, then RF, the row echelon form, also will have a solution, and those solutions will be identical. If RF, the row echelon form matrix, has a solution, then the augmented matrix will also have a solution, and the solution will be identical in both the cases. So we say that the augmented matrix and the row echelon form matrix are equivalent matrices. That means if one has a solution, then the other also has a solution, and the solutions would be identical. The next definition is what is called as the rank of a matrix. Rank of a matrix. And the rank is given as the number of non-zero rows in the reduced coefficient matrix. We had an original coefficient matrix, which is the A matrix, and after performing some row operations, we reduced that augmented matrix to a row echelon matrix. And in the row echelon matrix, we have this left part of the row echelon matrix, which is the reduced coefficient matrix. The number of non-zero rows in the reduced coefficient matrix R is called as the rank of the matrix. That means when we say non-zero rows, it means all the elements should not be zero. So in this particular case, we see that the first row has all of them to be non-zero. The second row has 2 elements to be non-zero, and the third row has 1 element to be non-zero. So we have in this particular case 1, 2, and 3. 3 rows in R which are non-zero. We consider it as a zero row only if all the numbers in a particular row of R are zero. Even if one of the numbers is non-zero, we consider that row to be a non-zero row. So if you look at this particular example, we have 1, 2, and 3 rows of R, the reduced coefficient matrix, which are non-zero. So the rank of this matrix is said to be 3. So in this case, rank of the matrix is the number of non-zero rows in the reduced coefficient matrix. Right? In this particular example, for the above example, rank is equal to 3, and rank is an important property of matrices to determine whether it is possible to solve the matrix or not, whether the solution exists or not. Now the next thing I want to tell is about how to interpret the final row echelon matrix. Okay, we can have different possible situations, and depending on what is the outcome we get in the row echelon matrix, we can interpret the result like we did earlier, whether the determinant is 0 or not 0. If the determinant is not 0, we said that the matrix or the equation has a unique solution. If the determinant is equal to 0, then it could be that either there is no solution or there are infinite possible solutions. So similarly, by looking at the row echelon matrix, we can determine whether this system of equations has a unique solution or not, or if not, whether it has no solution or it has infinite possible solutions. So we can interpret that from the row echelon matrix, and we will discuss that. For example, in this particular case, we have we do not have a complete row in the row echelon matrix which is 0. So you see here, at least one of the numbers is non-zero. So this is said to be a consistent system of equations wherein the system will give us a unique solution. So if this number in R, the last number in R in the reduced row echelon form, is non-zero, and this is also non-zero, then we say the matrix is consistent, or the system of equations is consistent, and it has a unique solution. If, for example, the this last number in the reduced coefficient matrix R is 0, and the number in the F vector in that particular row is non-zero. So suppose this is 0 and this is non-zero, then the system has no solution. That will correspond to a case where there is no solution. If the entire row is 0, that means this position is also 0 and this position in F is also 0, then the system of equations has infinite possible solutions.